good to go. So let me introduce myself first. My name is Sin-Kyu Nam, technical engineer of Midas IT. In today's webinar, I will briefly introduce you the basic procedure of post-tension PSC Box Girder Bridge using FCM, also known as free cantilever method and balanced cantilever method as per Eurocode. So the major objective for today is just to introduce you how to model the basic segmental bridges, post-tension PSC Box Girder bridges using both manual method and wizard method in Midas Civil. And then I'll show you how to check various analysis result and then the design report. So if you have any questions in between, I think I will actually go through some of the questions raised during the webinar at the end of the demonstration. So if you have any questions, so please do write it on the questions dialog box so I can answer it later on. So today I have prepared very simple PSC single box girder bridges. So this is the very simple PSC segmental bridges that I will show you how to model today. So as you can see, there is top view, and then you can see the slightly curved top view, and then the side view, and then the front view of the structure. As you can see, I have applied super elevations on the front view of the structure. The horizontal and vertical alignment of the structure will be created by importing the AutoCAD DXF file format. And then I will apply super elevations on the superstructure, and then I will extrude a pier 20 meters high. So I think most of you are already quite familiar with Midas Civil already, so I'm not going to go through every single details of general user interface of Midas Civil. So today's session will use taper section. So I have created a 2 PSC single cell section, so one with small opening and one with a larger opening. So I will use these 2 PSC sections to create these taper section, and then I will apply either linear or polynomial variations to create a nice smooth curvature of the taper sections. So taper section is used in this webinar, and then I will show you how to apply the super elevations on the superstructure in order to improve or enhance the quality of driving for the drivers on the structure. So you can use either change element parameter options in properties tab, I think element tabs, and then also you can change the you can just change the beta angle of the element from the element table. So once you create the basic geometry of the structure, you can apply various time-dependent material properties of the concrete material properties of the structure. So you can consider either creep and shrinkage material properties of the structure, and also compressive strengths of the concrete. So if you're using CEB FIP code or European code, you can select whatever the code that you are using in order to calculate those time-dependent material properties effect. And also the one thing that you have to be careful in this case is that you're using tapered section. So tapered section have a different depth along the girder. So the notional size of member will be different for every single element for the superstructure. So this can be inputted manually by the user using this input function. However, if you choose auto calculate, the notional size of member will be calculated automatically according to this equations provided. Moving on to tendon. So pretty much all types of tendons are provided, both internal and external, and both pre-tension and post-tension tendons are provided. So you can choose the tendon type, and if you need to consider the relaxation loss of the tendon, you can choose either CEB FIP code and European code, or if you have your own, if you have sort of your own data of the relaxation loss, you can just choose user defined and then use for your relaxation loss calculations. Creating the tendon profile in Midas Civil has various methods. We provide various features just to give more options for the user. So the first and the most basic method will be the tendon profile generator. So if you have your own sort of a coordinates information of the tendon in either 2-dimensional or 3-dimensional coordinates, you can just simply copy those data from Excel and then paste it onto this dialog box, and then you can have your own tendon profile for individual tendons. However, this can be slightly tedious if you have a large number of tendon arrangement for your sections. So another function is AutoCAD importing feature. So if you have your tendon profile in AutoCAD TXF file format, you can import this file onto Midas Civil, and then you can apply this onto the structures that you have in Midas Civil. And the feature that I want to highlight today is tendon template. Tendon template feature is creating some sort of a template file, template arrangement of the tendon. So if you go to this dialog box, you can see that there's a plan view option and elevation view options. So if I choose straight for the curved tendon, you can apply a straight line in terms of plan view, and then apply sort of a curved profile for the elevation view. And also you can define the number of spans, and then you can change these various parameters in order to sort of modify the profile slightly according to your design requirement. So once you create a tendon profile, one tendon profile, you can sort of move this and copy this around. And also you can create, once you create a large number of, once you create a whole tendon arrangement for a specific section, you can save this tendon template, and then you can import this whenever you want if you have a similar project or same girder informations with the identical tendon arrangement. So this can save a lot of time. This can save a lot of time for the generating those tendons individually. Moving on to construction stage. Construction stage is very simple and straightforward in Midas Civil. It is all about activating and deactivating certain groups. So let's say we have categorized this into 3 groups. So element groups, boundary, and the load. So at construction stage 1, you'll be activating certain structure group. And then construction stage 2 or 3, the following construction stage, you'll be activating another structure group on top of that. So those structure group activated in the previous stage will be accumulated, and then this will go all the way to the end until the cantilever finishes. So this applies exactly the same for the load and boundary conditions as well. The moving load analysis in Midas Civil is done in 3 steps. The first step is selecting the moving load code. And the second step is you need to sort of define the traffic line lane or traffic surface lane onto the structure. So if you're using a line element or frame element for your bridge, you'll be creating traffic line lane. And if you have a plate element for the surface, 2-dimensional plate element, you will be creating traffic surface lane. And then the final step will be that you will be creating standard vehicles, and then you'll be assigning those vehicles onto the traffic lanes that you have created. So if I have selected Eurocode for the moving load code, you can select various vehicles according to the standard. So for instance, load model 1 for Eurocode, those axle loads and UDL, those values are provided from the code. And then this is, as you can see, these values are already implemented in the software as a database. And also factors like adjustment factors or side factors, these are provided automatically with the default value using the recommended value from the code. Similar to the load model 3 with the UK National Annex, this is already implemented in the software as well. And also for the dynamic amplification factor, if you need to consider this individually, you can just use user input to input this dynamic amplification factor manually. And also you can consider this automatically based on these equations. Once you have defined the traffic line lanes and then the vehicles, you can assign the vehicles that you have created onto the specific lanes that you have created on the structure. So with this, you can select a specific load model and then just assign the vehicles that you have created and then move those traffic lanes that you have created onto this middle box. And when you create the load combinations automatically later on, you can also consider various load types automatically into the load combinations. Both seasonal temperature and temperature gradient can be applied to Midas Civil very conveniently. Seasonal temperature can be applied using element system and nodal temperature function in Midas Civil. You just have to define the initial temperature and then the final temperature, and then you'll be this will be assigned onto the structures as well, like a self-rate. And temperature gradient, either linear temperature gradient or nonlinear temperature gradient, can be applied using temperature gradient function or beam section temperature functions in Midas Civil. So if you're using PSC section, choose PSC or composite for your section type. And then you have to define the reference positions to be either to be top of the section or bottom of the sections. And then you can choose to define whether to consider the width of the sections automatically, or you can input this manually. And also you have to define the position of the temperature gradient, H1 and H2, and then the corresponding temperature value, T1 and T2. So what Midas Civil does is we do not calculate these values automatically. So user have to calculate these values manually and then put these individual temperature values into Midas Civil, and then program will do the rest of it. Moving on to result. So once you perform the analysis, various analysis results can be obtained in graphical format and table format as well. Apart from those general results, you can also, for this kind of project, like PSC sections, you can obtain those member forces analysis results at various different positions within those cross sections of the PSC sections. So as you can see, there are various stress points within this section. So if you choose position 1, you'll be able to obtain those member forces result based on the position 1 top fiber. And then if you choose position 3, you'll be able to obtain those analysis result according to the bottom fiber of the sections. So once you check all those analysis results, you'll be able to obtain those design report by specifying those various partial factors, so you can obtain various analysis, various design results, such as per ULS checks and SLS checks. And I will show you more about this later on during the demonstrations. So apart from those general features, there are a lot of other features useful for the balanced cantilever or PSC section type project. So effective width of the sections can be calculated automatically. And camber result. So in order to make the displacement 0 at the end of the construction stage, you can perform a camber analysis, so you can obtain those camber results. And also you may want to update these camber results onto your model. And you can do this by considering camber for construction stage function in the load tab under the construction stage load. And also you can obtain transverse analysis model from the global analysis model. So what you have to do is, for instance, if you have this sort of a global analysis model, you can select those, you can select specific sections, and then you can perform, you can bring this onto a transverse analysis model. And then what the program will do is it will sort of generate a separate model file in order to consider the load, the member force distribution according to the load distribution in the transverse directions as well. So I will quickly show you how to model this using manual method. So this is the general user interface of Midas Civil. So I think pretty much most of you are already aware with the general user interface. But let me just quickly go through the GUI again. So at the top there are various ribbon menu where you can obtain all those functions, and at the side you can obtain those tree menus where you can access all the informations of the model. So our basic procedure goes from left to right in Midas Civil. So you have to create those basic geometry of the structure first, and then you can assign various materials and section properties onto the geometry, and then you can apply boundary conditions to the structure, and then various load conditions onto the structure, and then you can perform various analysis on single model file. You don't have to separate a huge number of model files to perform different analysis. And then you can check various analysis results, and then check those analysis result member forces compared to the design requirement that you have. So I have prepared a very simple start model file, which I have previously defined those material properties for the superstructure and substructures, C40, and then those steel material properties for the tendons. Moving on to section, so I have defined a pier section, a box section for the pier, and then a very simple single cell PSC section for the superstructure. So one with the smaller opening and another one with the larger opening. So I'll be using these two sections to create the taper sections. So let's go to add, and then if I go to the tapered tab, you can select PSC one cell, and let's call it as taper 1. And then let's just import those taper sections that you have created already. So another thing that you have to note is that you will be creating the tapered section. So I'll change the section offset to center to top. So this will create the node at the top of the sections. The reason why I'm doing this is I want to make all those tapered sections nicely aligned at the top of the sections. So let's create another tapered section. Exactly the same geometry, but completely symmetrical. So one with the bigger opening at I end and one with the smaller opening at J end. And let's click OK. So now I want to create the basic geometry of the superstructure by importing the AutoCAD DXF file format. So I have prepared this AutoCAD DXF file, which is just a single line generated from the AutoCAD. And now I will basically assign these material properties and then the section properties onto the line that you import from the AutoCAD. So if you click OK, you can see that these line information has been assigned with the material properties and the section properties that I have in my model file. So now I will assign tapered sections onto this. So let's just select half of it, then simply use drag and drop feature to assign these tapered sections. Now what you have to do is you need to sort of make this tapered sections into a single group. So we need to go to tapered group option. And let's just call it as taper 1 element. I've selected this already. And I want the variation to be nice smooth curvature. So I have selected polynomial and I will click add. So you can see this taper section has been created relatively conveniently using this. Now I will do the exactly same for the other side as well. This time the variation will start from the J end. So let's select J end and click add. Okay, so you can see that the superstructure has been created nicely. Now I want to create the substructures. So let me create substructures from the bottom of the PSC sections. So I will translate the node -6 meters downward, and then maybe around -2.5 meter. So I will basically create an abutment support at each end of the balanced cantilever. So there are various options to create the models in Midas Civil. So this time I will use extrude function. Using extrude function, you can extrude line element from node, plane element from line element, solid element from planar. So I will choose node to line element. So material property C40, section properties for the pier sections, and I will create the piers 20 meters downward, 0, 0, -20, and I will click this node and then click apply. So you can see I have created the pier sections from the bottom of the PSC sections as well. Now let me apply fully fixed boundary conditions at the bottom of the pier, and then let me release rotational and the X direction constraint for the abutment structure as well, abutment part as well. So I have finished applying the boundary conditions as well. But if I turn off the hidden view, you can see that the superstructure and substructure is not actually rigidly connected. So I will sort of connect these using elastic link rigid type. So you just have to click this to node, and for the other side as well. So you can see that I now have the superstructure and then substructure connected rigidly. So this is pretty much it for the generating basic geometry of the structure. Now I will be assigning time-dependent material properties onto this structure. So let's go to Properties tab and then go to Creep and Shrinkage and click Add. So let's just call it as C40. And then if you're using CBFIP code, you can use this. Or if you're using European code, you can use this as well. Before this, let me just quickly change the unit system into Newton millimeter because I'm using megapascals. So I'm familiar with Newton millimeters. So let's just call it as C40 and then select European. And then what I will have to do is I will have to assign 40 megapascal characteristic compressive strength for this concrete. And then, as I mentioned, the notional size of member has to be defined. However, you know that the depth of the individual taper section is different for every single element. So I will have to sort of assign any sort of initial value. Obviously, this will not be the same. However, there is a function in Change Property tab where you can calculate the notional size of member automatically. So what I will do now is I will just assign any sort of initial value for the notional size of member. It doesn't matter, because you will change this later on as well. So if you check the result as well, then you can just simply click OK. And let's create compressive strength of the concrete as well. And select European code, C40 again. And the mean compressive strength of the concrete, FCK plus delta F, which is 48. And there's the graph result. And then click OK. So now what you will have to do is you need to go to material link. And then you need to select those time-dependent material properties that you have created. And then you have to assign these normal concrete material properties that you have created at the beginning of the project. So what this means is that whatever the element assigned with these material properties will be having this time-dependent material property effect. So if you are considering the construction stage later on, the time-dependent material property effect, creep and shrinkage, and compressive strength will be automatically applied onto these elements. So I have now have to consider the notional size of member. So let's go to change property, and then there's a notional size of member, auto calculate, and then you just have to select all the element and then click apply. So if you click this button, you can see that the notional size of member for every single element has been calculated, and then this using these equations specified here. So now let's move on to the load, applying load conditions. Let's create load cases first. So let's just create self-weight and define as construction stage load type and click add, and let's define pre-stress as well. And then excuse me, the temperature load type as well. So by selecting these different load types, you will be able to obtain those load factors applied to the load combinations automatically later on. So this is why we separate these load types as well. So let's close this. So self-weight can be applied onto the structure through this function. So you just choose self-weight and apply self-weight into -1 in Z direction, and I click add. And let's go to the tendon. So tendon you need to define the tendon property first. So let's click add, and then name as tendon. And then you just have to select the tendon type. So let's choose internal post tension, and then click the material properties that you have defined at the beginning. And then you can also define the number of strands as well, and strand diameter. Using this, the total tendon area will be calculated automatically, and apply dot diameter as well. Similar to the time-dependent material properties, the relaxation loss of the tendon can be calculated according to various standards. So if you're using CBF IP code, you can just select this as well. And then let's click OK. And now we need to create a tendon profile onto the structure. So if you have your tendon coordinate information in terms of 2-dimensional or 3-dimensional coordinates, you can sort of input this. You can sort of copy this coordinate data from the Excel and then paste it onto this dialog box right away in order to generate individual tendon profile of the structure. But today I want to show you how to consider generating tendon profile using tendon template feature. Let's open the tendon template dialog box and then select all the girder groups. So all the girder element has been imported straight away here. So this is automatically imported. And if you click add, you can see that a general profile of the tendon in terms of plan view and then elevation view. So if you choose straight for the curved tendon, you can choose this. So you can see that the plan view, it is straight line. And then if you go to elevation view, you can see that this is curved as well. So if you define the number of span, you can sort of define this in terms of different span as well. So if you're using this option, same span information, the span will be divided exactly at the half of the whole length of the girder. But if you can also specify those distance as well individually. And by changing these parameters, you'll be able to modify those tendon profile manually. So once you create this tendon profile, and then you can just click OK, and you can see that those tendon profile has been imported onto this dialog box. And then what you can do is you can sort of move this and copy this around as well. And once you created whole tendon arrangement, the good thing about this is you can save this by using if export function, and then you can save this as a tendon template, and then you can use it at any time later on. So I have saved a simple tendon arrangement for this 2 tendon profile at either side of the girder, and I'll just quickly click OK. And you can see that tendon profile has been generated according to whatever the tendon template that I have created previously. So this is the tendon template, tendon profile generated with the tendon template feature. The good thing about this feature is if you have sort of a PSC composite girder bridge design, you'll be having more or less the identical tendon arrangement for all the other girder groups. So you can create one tendon arrangement for one girder, and then you can sort of copy this onto other girder groups as well. So you can save huge amount of time generating tendons individually. So let's move on to creating traffic load, the moving load onto the structure. You have to create the moving load code. So I have selected Eurocode. Let's create traffic line lane onto the structure. Let's call it as line 1. And let's create traffic line lane 4 meters eccentricity from the center line of the structure. And then if the girder element is a straight line, you can just simply use 2-point option by selecting start position and end position of the element. However, if the bridge is slightly curved, you can just simply input this element by using element number and then click add, then click apply. Then you can see that traffic line lane 1 has been created. I will do exactly the same at the opposite side of the reference line. Now click add again and click OK. Now you can see that 2 traffic lanes has been created at either side of the sections. So traffic line 1 has been generated from 4 meter eccentricity from the center line, and lane 2 4 meter eccentricity at the other side of the girder. So now what we have to do is we will create moving load vehicles from the standard. So load model 1. So all these parameters are already explained from the presentation. So this can be provided in terms of standard vehicles. Click apply, and load model 3 as well. You can actually annex various special vehicles. And if you click OK, you can create those vehicles. So if you go to user define, you can sort of modify all these values, adjustment factors and side factors for this load model 1, load model 3 as well. So you're using user-defined vehicle types, you can create pretty much more or less any vehicle types that you can think of. So the next step is you need to create the moving load case onto the structure. So let's just call it as moving load 1. And what you will have to do is you just have to select the moving load vehicles that you have created just now, and then you have to select those specific lane informations that you have created. And then what you are doing is you are assigning these vehicles onto the lanes that you have created. So now I have created a moving load case as well. Let me quickly show you how to create the temperature load, and then let's move on to the wizard feature. So the element temperature can be applied here. Let's just change the unit system into Celsius. So if you go to load tab and then temperature, the seasonal temperature can be applied very conveniently by changing the initial temperature and then the final temperature. Just apply onto the top of the superstructure. And then the beam section temperature can be applied using this feature, PSC, and then you'll be able to define the reference position to be top of the section or bottom of the section. And then you can manually define the width of the position of the temperature variation, or you can just choose to consider this option as automatic. And then you will be defining those position of the temperature variation and the corresponding temperature values. So this is pretty much it for the manual method of PSC box girder bridges, but let me quickly show you how to consider construction stage, and then let's jump onto the wizard feature. So in order to consider construction stage, you need to have a structure group, boundary groups, and load groups. So let's create a structure group 1 to 10. And click add. So what you have to do is you need to assign these structure group and all of it. So this can be very tedious. So let's just do it up to structure group 6. And then let's go to load tab and then go to construction stage and then define construction stage. Or let's just go to the shortcut. So let's generate our construction stage, CS 1 to 10. And then you can define the duration of each construction stage as well. But you can change those durations later on as well. So if I click OK, I have created 10 construction stage. So if I go into construction stage 1, you can sort of activate structure group 1 and then click apply. Let's go to construction stage 2. Now structure group 1 is already activated. Unless you deactivate the structure group, it will be at the same positions. So let's do this up to construction stage 6. Construction stage 5, structure group 5, and construction stage 6, and structure group 6. And let's click OK. So if you go to this combo box, you can select those construction stage. So if I click construction stage 1, you can see that construction stage 1 and structure group 1 has been activated, and construction stage 2, structure 2 has been additionally activated as well. Construction stage 3, 4, 5, 6, it goes all the way to the end. The one thing I have actually forgot about this is creating those super elevations on the superstructure. So if I have sort of angle informations, so 0 to 5 degree, 25. So if I go to the node and element tab, you can change the super elevation by changing the element local axis, beta angle as whatever the angles that you define, and then just select those element and then click apply. Or you can go to the element table, and then you can simply assign this beta angle onto the structure, and then you'll be able to see that those super elevation, the beta angle has been applied onto the substructures. Okay, so this is it for the manual method of the manual method part. So let's quickly go back to the presentation. So using manual method, you have seen that we have defined materials and section properties of the model, and then we have modeled the structure, then define and compose various structure group, boundary group, and load group in order to create the construction stage analysis model. And then you can create various load information such as moving load or temperature load from this. And then we have also created tendon arrangement for the PSC section. And then we have defined those construction stage as well. So all of this can be done in manual method without any limitations. However, if the structure is very complicated and if you need to consider various other stuff such as bearings and curvatures, this can be quite tedious. So we provide another feature called FCM wizard, free cantilever method wizard. So all of these procedure can be done in one step in the wizard feature. And the good thing about this is you can save this wizard as a wizard file, and then you can import this later on at any time, like a Tendon template. So let's go to the start model file for the wizard. So I have prepared exactly more or less the same start file for the wizard. So let's go to the structure tab and then go to FCM bridge function. So this is the basic user interface of FCM wizard. So there is two options, type 1 and type 2. This is more or less the same, but type 1 is the method that you will be creating those FCM bridge using this template or the form, or we can say the form provided by Midas Civil. So model tab and section tab and tendon tab. So you'll be creating those PSC balanced cantilever structure following this template. However, if you go to type 2, the model tab is the same because it's all about geometry. But if you go to the section, so if you have your own generalized section, you can create your own sections using this. So if you have any section drawing in AutoCAD, you can import this AutoCAD section file onto Midas Civil SPC function, and then you can use this whatever the sections that you have as your own sections in PSC Girder Bridge project. And same for the tendon as well. So those tendon arrangements can be created by manually using this option. But today we'll be sticking on type 1 method. So let's go to each and every model tab, section tab, and tendon tab one by one. So model tab is all about creating the basic geometry of the structure. So at the top, we have a box for the superstructure. So defining materials and section properties for the girder and the pier. And the pier sections can be defined here as well. Then you can define the stage durations. And then you can also define the number of piers as well. And if your alignment is slightly curved, you can apply radius of the curvature in order to create the curvature of the structure. And also you can define those geometry for the substructures as well. So this is the substructure part, pier table and key segment. So pier table width, and then those diaphragm spacing, and then the key segment the length as well, and then the pier height, and then the pier spacing, the column spacing, and FSM and zone 1 and zone 2, you can define individual segment length. So let's say 2.4 meter, 2 of them, followed by 4.2 meter, 2 of them, and so on. So you can define those each and every segment individually using these options. So model tab is all about creating basic geometry of the structure. And then if you move on to section tab, you can create either 1 cell or 2 cell taper section of the PSC sections using these parameters. So you can check this with the drawing view options as well. And also form traveler can be considered using this function. So any eccentric loading or eccentricity moment created due to the form traveler can be considered using these options. So it will be applied as a nodal load at the end of the cantilever. And moving on to tendon, you can define tendon properties for the top of the section and bottom of the section. And then you can define the pre-stress, the checking stress, to be either 70% of the ultimate tensile strength or 70% of yield strength of the tendon. So you can choose this as well. And then you can define the tendon anchorage number as well for each and every segment. And then at the right-hand side, it shows the specific locations of each tendon, and the tendon numbers as well can be defined. as I have mentioned, so once you import all these parameters, you can sort of save this as a template, and then you can import this at any time later on. So this is my input values that I have inputted previously. So I have saved this file, and then I can use this at any time later on. So if I click OK, the program will automatically consider the construction stage as well. So the whole overall structure will be created, including those construction stage and various load cases applied onto the structures as well. So if you go to construction stage 1, you can see that tendon profile. Let's display the tendon profile. You can see that tendon profile has been generated at every stage of the construction stage. And let's just deactivate this. And then let's activate the form traveler. If I display this, and you can see that the form traveler is activated at the end of the construction, at the end of the balanced cantilever at every stages. Okay, so the moving load is cannot be created using this wizard file. So you have to create moving load and then the temperature load after generating the model file from the wizard. So once model file is generated from the wizard, any sort of modification is possible. So you can sort of play around with this, then you can change any modifications on the model. So I have performed the analysis on this model file. So let me quickly go through what sort of analysis result that we can check for this model file. So first of all, I'll show you just basic reaction result. So if you're not familiar with this, you can go to the result tab and select reaction, and then you can select specific load cases or load combinations, and then choose the component, and then you can also choose the type of display as well. And let's just change this to kilonewtons per meter. And then you can obtain this reaction result as well. And also you'll be able to obtain those results in table format using this buttons. So these are the reaction results at all the support positions. And bending moment result. So if you want to check the bending moment result at construction stage 10 due to the summation of the load cases, you can sort of select specific construction stage in order to review those member forces result at different construction stages. And also this can be reviewed in table format as well. So you just have to select the load cases or combinations and specific stage, and then you'll be able to obtain various member forces result, such as axial load, shear force, torsion, and bending moment, and so on. Let me show you about the moving load analysis result in Midas Civil. So let's go to the result and then the moving load part. So let's choose influence line. So basically, the moving load analysis in Midas Civil is done by influence line analysis onto the structure. So what it means is we apply unit load onto the structure and then obtain those influence line analysis. And then what program will do in terms of moving load is that you have to select the key element as well, identical key element, and let's select bending moment and then moving load maximum. And let's click apply. Let's click the legend as well. Let's turn off the load value. So the program will automatically position the vehicle at the most critical positions based on the influence line analysis result. So for the key element number 30, the maximum bending moment result is 18,000 kilonewton meter for these vehicle positions, and for shear force, it's giving us 622 kilonewton for this specific vehicle position result. The good thing about moving load analysis in Midas Civil is you do not have to sort of make many different scenarios for the different vehicle positions. So you don't have to have a huge number of moving load cases in order to find the critical positions of the vehicles and corresponding the member forces result. So let's check these values that we just checked from moving load tracer function from the beam force diagram. So let's go to the table format and let's select element 30 and select moving load case maximum. Let's just select part type. And you can see that there was shear force 622, which was this 622 kilonewton, and then the maximum bending moment is 18,000. However, when we go into the design part, we do not want to use this sort of envelope result, because even though these forces are maximum result, the forces does not happen simultaneously. So these forces will have individual vehicle positions. So these forces is not concurrent actually. So if we right click, we can go to view by max value item, then click shear force, and then the bending moment, and then we can choose those maximum moving load case. And if we click OK, we can obtain those results when shear force is maximum for key element 30, which was 622. We can obtain those member forces acting at the same time with these specific vehicle positions. And if we say when bending moment is maximum, which was 18,000, we can obtain those analysis results acting at the same time. So these are the concurrent forces that you might be interested in terms of design. So this is provided by Midas Civil. So you just have to go to analysis and then check this option, normal plus concurrent force option, prior to the analysis. Moving on to tendon loss result, I want to show you. You can specify a specific tendon at different construction stage, and if you click apply, you can obtain those tendon loss result in terms of table format. So short-term loss such as anchorage slip, or long-term loss such as elastic deformation or creep and shrinkage or relaxation loss of the tendons can be obtained in terms of both table format and then the graphical format from this. So you can define whatever the construction stage, and you can choose whatever the tendon as well. So once you check those tendon loss result, you may also want to check those tendon stress limit check without having to go further into details in terms of design. So if you go to result table and then tendon stress limit check, you'll be able to check those tendon stress limit at the anchorage and across away from the anchorage and at the service conditions. You'll be able to obtain those stress limit value and then corresponding tendon stress analysis result. So let's just wait for a bit. Okay, so click OK. So all the tendon, and you can define the tendon stress limit. These parameter values as well. If you click OK, you'll be able to obtain all these tendon stress limit values, and then those tendon stresses acting for individual tendons are specified at the far left. So tendon stress limit checks can be obtained in Midas as well before going into the design. And also you'll be able to obtain those stress or member force distribution on the girder using bridge girder diagram function. So if you go to construction stage 10, and if you want to review those analysis results due to the summation, and combine the stress result at this position, and also we can select allowable stress line. So allowable compressive stress or allowable tensile stress can be specified here. And then if we check this option, line of these values will be represented on the graphical result at the same time. So as you can see, these are the summation, these are the combined stress result due to the summation result. And you can see that there was allowable stress line, allowable compressive stress and tensile stress line is specified here. And then those stress values are falls in this range, so it should be okay. So once you check all these specific analysis results, you can perform the design as per Eurocode. So let's go to the PSC tab, and then you can select, you can go to parameters, you can select this parameters option. So let's just go to the PSC tabs, and you can select the code as Eurocode. And then you can see that design code for Eurocode and National Annex for British National Annex is provided in Midas. And if you go to this modified design parameter option, you can select various different parameters for the design feature based on the Eurocode. And you can change all these features, or you can sort of update this by the code using the recommended value from the code, Eurocode 2 or British National Annex. And you can also perform the design by checking the ULS checks and SLS checks. So if you don't want to perform SLS checks, you just have to uncheck these boxes and then only check these ULS checks box. And then close this. And then what you will have to do is you will have to define the design position. You have to define where to design the structure, and then define the output position of the design result. And then if you click serviceability load combination type, so if you have created those load combinations automatically in Midas, the program will automatically sort of sort to all the load combinations into these 3 different categories automatically. However, for those load combinations that you have created manually, you can still sort of separate these load combinations manually into these 3 different categories for the serviceability load combination consideration. And also you can, once you check all these features such as exposure class for the cracks or shear connectors, once you have defined all these input features, you can perform the design. Then you can check the design result in terms of table format as well. So if you go to design result, check flexure strength, you can check those capacity result, and then the bending moment acting at the element. So you can check the bending moment capacity of the section, then you can check the bending moment acting at the sections at the same time. So none of these results are outputted as red. So it means it is fine. It falls within the capacity region. So all this bending moment acting on the structure is fine. So you can check these analysis and design results in table format, and then you can output these design results into Excel report file as well. So once you output this Excel report file, you can obtain Excel file like this. So you can access all the informations about the model, about the sections, and these are the parameters that you have defined in the design parameters options. And then for ULS checks, so positive moment, so all these checks are provided, and these are all from the Eurocode. So all these analysis and design results are specified in this Excel report. And then the good thing about this is specify which part of the code that Midas Civil is using in order to obtain this analysis result. So this is quite large value, so this is fine. So you can sort of go through the manual calculations of your design result, and then sort of cross-check the design result from the Midas Civil and manual calculations from your side. So you can sort of cross-check those analysis results, and you can get confident with the output result from the Midas Civil. So this is it for the brief explanation of the PSC Box Girder Bridges in using both manual method and wizard method in Midas Civil. Before finishing off, I just want to show you some of the frequently asked questions, so FAQs for designing this kind of bridge types. And let's finish off with some of the Q&A sessions. So I got a few questions received from the UK clients asking about how to check section properties of the tapered section. So once you create the taper sections using this taper section group option, you will have one taper section which represent this whole lot of the element. So if you double click this taper section, you will be getting this whole taper group at the same time. So you'll be only getting those section properties result at each end, I end and J end here. However, in order to obtain those section properties at every position of the tapered section, you can sort of divide this tapered group into individual tapered section using convert to tapered section option in this function. So once you do this, these tapered 2 sections will be divided into all of these individual tapered sections. So you'll be able to create a large number of section informations. And then you can check those section properties at every positions within this locations. And also, I think it applies to all the other finite element method software as well. So all the analysis result in Midas Civil is calculated at the neutral axis. So this becomes problem with the tapered sections. So if you think about it, the neutral axis of the tapered section is not parallel to the node information. So the neutral axis will be slightly lower at the larger opening. So the perpendicular line will be slightly slanted, and then the analysis result obtained from this will be not from the parallel to the end of the section, So in order to prevent this, in the main control data, so main control of the symbol. So if you go to analysis, and then if you go to main control data, you can see this change local axis of tapered section for force/stress calculation. So if you select this option, you will be able to calculate those member forces result at the parallel to the end of the tapered sections. And also reinforcement for the tapered sections can be considered using section and reinforcement tab. So you just have to apply the cover length, and those longitudinal reinforcement will be applied onto the tapered sections, even though it is the depth of the section is different for the other element as well. And if you go to section manager, these reinforcement applied from this function can be modified individually. So you can use this feature as well. And also for theoretical calculation of tendon elongation can be obtained using this result table. So result table, tendon and tendon elongation, you'll be able to obtain those shrinkage informations of the tendon and the concrete itself can be obtained. So this can be provided to the constructor, maybe as a reference material for the actual construction job. So this tendon elongation result can be obtained as well. So thank you for joining our webinar today. So if you have any questions, I will answer this as much as I can. And then for those questions I cannot answer, I will answer all those questions from the email. So if you have any questions, please send us onto the UK support at midasuser.com. So I have received one questions about transverse analysis. And I actually have prepared this as well. So let's go to the structure and then go to the transverse model. And what you have to do is you have to select element. So select element from the global analysis model, and then you have to define the input values for all these pavement and barriers, all these superimposed dead load features, and then those the length informations as well, and the load for the pavement, self-weight, barrier, median strip, and all these live load informations as well, and also wind load information if you need to consider. And pretty rare case, but if you have transverse direction tendon or reinforcement, you can apply it to this as well. So you just have to click define, and then if you export this, you'll be able to create those separate model file. So you'll be able to have separate model file, something like this. So you can see that those temperature gradient or system temperature or collision load or barrier informations or the pavement, and also live load informations. Live load data in terms of transverse directions can be applied here. So you just need to have to perform the analysis on this and then obtain those results. So displacement contour according to the self-weight. So all this analysis result can be obtained as well. And okay, so one question from Rachel Harry. So he said, is it possible to apply traffic light name to the curved structure? Yes, it is possible. And those, okay, so those nodal local axes, this is applied onto those support for the curved structure, because, you know, if we obtain those reaction results according to those global axis direction, this will not be exactly the same that we want, because this will not be the perpendicular or parallel to the, the tangential direction of the curvature of the structure. So what we want is, we want the longitudinal direction and transverse direction at the positions of the curvature. So that is why we are applying the node local axis onto the support position, and this is automatically considered in Midas Civil if you're using a widget. But you can also apply this using node local axis options, and you can apply sort of specific angles about z-axis, and you can just choose these individual support conditions. So if you go to the result, and when you're checking the reaction, let's call it, and let's say if you're checking the reaction result, the reaction result here will be actually in terms of global x and global y direction and global z direction. But if we choose this local option, if defined, it says, and if you click apply, those analyses will be obtained from the local axis that you have defined. So this is actually these reaction result is actually what you need, not the reaction result from the global axis. And another question is from Joseph. So what's the difference between a rigid link and an elastic link of the rigid type? So basically, the origin of the elastic link, rigid type, and rigid link is slightly different. So you can almost think this. You can almost think rigid link as an element. So we are applying a very huge stiffness value for the elastic link rigid type. So if we consider the elastic link rigid type, we are actually considering the stiffness values to be very large. But for the rigid link, we can almost think this as a separate element. So if we select master node and slave node from using the rigid link, so master node and the slave node, so this will be sort of connecting those master node and slave node sort of as one element. So if master node moves to the x direction, slave node should be moved to the x direction as well at the same amount. However, elastic link rigid type is slightly different. It is applying some sort of connections with a very large stiffness value. So in fact, the rigid link and elastic link rigid type will be more or less behaving pretty much same, but the fundamental origin is slightly different. So Andrea has asked us about the beta. Is the beta angle can be assigned to the tendons as well? Unfortunately, beta angles cannot be assigned onto the tendon because beta angle is element property. However, the tendon in Midas does not consider to be, so basically tendon in Midas is not an element. So we cannot apply a beta angle onto the tendon profile. Okay, so I think I have 2 more questions. I think this should be enough for the time being. And I have questions from Mr. Hong, and I think I will answer this via email. So thank you for listening to the webinar today. So thank you for joining, and I hope you guys enjoyed. So thank you very much. So if you have any questions, please email onto this uksupport@midasuser.com. And if you want this webinar material, we'll be able to send you the PDF, PowerPoint, and the corresponding model files as well. Thank you very much.